All right, guys. Can you hear me? I'll try to adjust this thing. It's giving me troubles. OK, let's get started. As I just been said, my name is Peter, network engineer at Facebook. The topic of my talk is identifier locator addressing, ILA, and specifically the application to virtual networking. All right, so I begin by saying that the whole concept of virtual networking is confusing. There is so many technologies people use on the host right now, mostly overlays, JRE, NVJRE, VXLAN, I think Geneve. With so many encapsulations and control planes, it's really hard to track what's going on and why people do this. So we started by looking at the problems we're trying to solve at Facebook with our approach. So first of all, containers. Containers are really hot right now. Like, it's as big as VMs were like a few years ago. Everyone likes them. I guess everyone knows what Docker is, what Kubernetes is. People love this because it's lightweight, it's easy, and seems like to be really efficient. We do have this at Facebook as well. Not Docker necessarily. It's our own implementation. But this is our approach to virtualization on the host. And there are two main problems you encounter in networking space with containers. The first one is the fact that you may run lots of containers on one machine. Sometimes 2, sometimes 10, in some cases up to 100, for example. And these guys have to share the IP address of a machine in some way or another. In most cases, people either have to allocate multiple IP addresses per machine or reuse port numbers across processes. Both cases are a little bit problematic, especially port allocation. Second one, which is specific to Facebook, was mobility. When you move a task to a different machine, which often happens on rescheduling, you will have to change the IP address of the task, or the process in our case, or container. I keep saying task because we call containers as tasks at Facebook. OK, so these two challenges require us to address two different goals. First one, being able to allocate IP address per process. On the slide, it says IPv6, and it's serious IPv6 because we don't use IPv4 internally, almost. In case of our containers, probably every single process uses IPv6 addressing only. Our goal was to be able to allocate unique address per Linux process. Secondly, address mobility. We wanted to let address follow the task or process when it changes a machine. It's not like really necessary, but it simplifies a lot of functions in our internal backend systems. OK, so two goals, address per process and mobility. So ILA was one way to address this, and this is the solution we deployed so far. ILA is built on the old, well-known concept of identifier and locator split. I guess everyone, well, maybe someone, heard about these abbreviations before. ILNP, GSC, 8+8. This used to be a very hot topic in networking probably 10 years ago when they had these discussions about internet table scaling. There was multiple proposals. ILNP was one of them. So you may think of ILA as a technology which builds on ILNP. So the way it works is pretty straightforward underneath. You have this 16-byte address, IPv6, and you split this in two halves. First half is called the locator. Locator is 64-bit long. It's used for routing lookups in the network. It may change over time over the course of the life of the address. The second part is identifier. Identifier is a kind of a name of a process that has this IP address. It's immutable. It's given to a process on the start. It doesn't change. So the way ILA worked is that it required that every node or host in the network had a /64 prefix, not an address, but a prefix. Secondly, as a process would migrate between machines, its ILA address, this 16-byte entity, would change the locator field. It's a very simple concept. It says, OK, these first 64 bits identify the anchor, the location, and the rest is the name. However, in case of previous solutions, like ILNP, the requirement was that the changes in the locator were visible to the transport or applications, which meant you had to change TCP code or Linux stack or any other networking stack to accommodate for these changes. And I think this was probably the biggest problem with LNP. This need to change the transport stack was really kind of impossible to implement. So ILA kind of works around this limitation. It hides locator changes. So basically, it makes transport layer believe that the locator field never changes. It looks like it's one fixed value, one fixed 64-bit entity that never changes. The way it does it is by doing a stateless NAT underneath the transport layer. So every time you receive a packet, it will have to be rewritten back to have a fixed locator. So ILA hosts naturally have to have this /64-bit prefix allocated to it naturally, like any of these ID log split solutions. Of course, every host has to maintain a mapping from the identifier to locator to tell where a particular name or ID is being now located. And lastly, ILA adds one new concept called ILA router. It's a special proxy, a gateway, that allows the non-ILA machines to talk to ILA machines. If you remember, LNP was requiring that every machine was modified to support LNP. ILA works around this process by mediating or adding this additional ILA router that allows the ILA world to talk to non-ILA machines. OK, so this is an example of how this whole NAT thing works. Imagine you have this prefix. It's called SERP prefix. I'll explain this a bit later in the next slide. But this is the 64-bit locator that remains unchanged in the ILA address. So we have one ILA host on the left, on the slide left, right? So it has a process which has the ILA address. The entity in orange is ILA address, the Facebook 1234. Facing book is the special fixed locator. And 1234 is the name or ID of a process. At the same time, this host has a green address, the locator. This locator identifies the position of the host in the network. Symmetrically, you have the other counterpart, the host with different locator and different ILA address. So pay attention, the ILA address belongs to a process, and the locator belongs to a host. Now we have process 1 setting packets to process 2. As you can see, both fields, I think they are unfortunately truncated in the slides. But the source and desk addresses, they both have ILA fields. So the orange untranslated names. As they hit the wire, we rewrite the locator portion with the actual physical locator. What happens now is that network knows to transport this packet to the other side where you have the other locator. On the other side, you do reverse translation, and you write these physical locators, the green fields, into the orange ones, into the SERP prefix. And so in this way, the NAT prevents the applications from seeing these changing locators. They always see this one fixed prefix, Facebook. OK, so now back to this magical SERP prefix. As I mentioned, it has special meaning in ILA network. It stands for a standard identifier representation. This is the fixed preconfigured parameter for all ILA hosts. This is the locator seen by the transport. And most importantly, this SERP prefix is being injected into a IPv6 network by the ILA routers. This is necessary to be able to attract the traffic from non-ILA hosts into the ILA hosts. So you may think about this as this SERP prefix, this magical prefix, being a name of a subnet, one virtual /64 subnet, which is being shared by all processes running all machines. So looking at the left, you can see, let's say, all our containers sharing this one address space on different machines physically. And the ILA router acts as the gateway or the IPv6 router on this virtual subnet that provides communication between the processes and non-ILA world. Most importantly, this cloud on the left is virtual. It doesn't physically exist. is being formed by the processes running on tons of different machines. Okay, so next important concept, as I mentioned, ILA router. This guy is responsible for knowing of all ID to locator mappings in the network. It maintains full cache. It does inject this magical SORT prefix in the network to attract traffic from non-ILA hosts. In this way, it provides the mediation or proxy function between non-ILA and ILA world. And lastly, as we'll see on some other slides, ILA router also provides the gateway function between ILA processes in some cases. It's very important, I bring this analogy before, to think about ILA router as an IPv6, normal IPv6 router on this one virtual segment. It's a very useful analogy to understand how ILA works. Okay, now let's look at this diagram. We have what? We have 3 ILA hosts and 1 non-ILA host. The non-ILA guy is on the cloud, which is supposed to have IPv6 network, but it's truncated. The ILA router injects the SORT prefix, Facebook in this case, is not shown in the diagram, somehow got away. And non-ILA host send packet to ILA machine. So here's the key. The non-ILA host have no idea about all those mappings or identifies locators. It only knows that it has to send packet to the SORT prefix. And since this prefix is in the network, it got sucked into this ILA router. And now ILA router has a translation. So what it does the rewrite and sends the packet to the correct machine. The ILA host in turn, now, okay, packet is for me, it does a translation and responds back directly to the non-ILA host. For those of you who deal with load balancing, this looks very much like DSR, direct server return scenario, and it's by no mistake, it's a very similar concept. This also offloads the ILA router from the need to send traffic backwards to the non-ILA hosts. Now let's see how the ILA router may be used to help provide transit between ILA hosts. Same scenario, we have ILA router and 2 ILA hosts. So ILA router usually injects the SORT prefix, all this usual business. Now let's imagine that the ILA host on the bottom does not have a mapping. For example, cache is empty. What happens next? It sends a packet as usual, no translation, in the network. The packet gets sucked into the ILA router because of this SORT prefix injection. What happens next? Well, there's translation and sends back a redirect packet. Very similar to the IPv6 router, like ICP redirect, you tell the originator, hey, now use this mapping because it's available. And this allows the ILA host to shortcut and bypass ILA router for further interactions. So unlike the non-ILA hosts, ILA hosts may respond to redirect messages and install the mappings on demand. Okay, control plane. Control plane is necessary in ILA to mainly inform the ILA routers of all existing mappings. So good news, there is no standard, so you can mess around, actually invent some crazy things. It's a very good time to play with this technology. In our case, as I mentioned, there's only a few things you have to do. First of all, the ILA routers have to learn of all active mappings. Basically, we need to know where each identifier belongs to, which locator. Secondly, ILA hosts, by this virtue of this requirement, have to always inform the ILA routers of the active mappings as they change on the fly. Because remember, tasks can move, things may change, and you have to always update the ILA router. One very important thing about the ILA is the data plane assistance. They didn't exist in ILNP or any other proposals. This is very specific to ILA. As we've seen before, the ILA routers may send very direct messages. And these messages are being sent on demand. Not on demand, driven by data plane traffic. When you receive an entry, a packet, you will send back a direct message. It doesn't involve any control plane transactions. It's purely driven by the traffic. And in turn, the hosts themselves may also send redirects back to other hosts, telling them of stale entries. For instance, if a given host loses a mapping for ID and still receives packets for this ID, it may tell back to the originator, hey, stop, because I don't have this mapping anymore. and this will force the sender to invalidate the cached entries. Once again, the analogy to IPv6 is very, very clear. We currently don't use ICMP with UDP packets, but the concepts are very much the same. OK, now let's look at the most funniest part is the mobility, how we implement mobility using all this magic. All right, now the scenario, we have 3 ILA hosts. So we have an ILA stack, we have all those mapping caches. We have 2 ILA routers. So it's very important, you are not limited to just one ILA router. You may have 2, 4, 16. They can all inject the server prefix in any cast fashion. Now we have host C talking to host B using the ILA addresses. Like in this case, there's 2 processes, IDs are given on the diagram, they talk to each other. Now imagine that the process on host B changes its attachment, changes the location. What happens next is the job scheduler or container scheduler, it's speaking using the open terminology, removes this entry because task is gone. Immediately, our flow is now invalid. We hit the black hole, and host B sends back the invalid entry mapping. In this case, the invalid mapping is truncated, but this is essentially a message saying, hey, this mapping is now invalid. At the same time, the host, which now has the task, tells the ILA routers, I now have this mapping, update your caches. What happens next is host C falls back to the routers because it doesn't have any other option. There's no cached entry anymore. But luckily, the ILA routers do have this entry. They forward the packet down to ILA hosts. At the same time, they send back a direct message to the host saying, hey, this is the new mapping. And magically, flow now recovers and flows directly. So basically, driven by the data plane packets only, we've been able to switch over between the 2 flows. First one via the routers, and second one now goes directly. That's pretty much all the magic to implement task mobility with ILA. Once again, it's really important to remember that this whole real-time mobility is only possible because we use the data plane messaging. Using control plane signaling handshakes might be slower. In this case, relying on the data plane messaging makes it much more efficient and faster. OK, now the more serious part, deployment. Deployment at Facebook specifics, we've done how we progress so far. So first of all, as I mentioned, the most critical piece in ILA architecture, ILNP, or any other, is to allocate a /64 IPv6 prefix per host. That's the most difficult operation. So the diagram on the right shows you very simplified data center hierarchy, 3 levels: rack switch, pod, and like data center. So spine covers data center, pod covers like, say, 1 cluster, and rack covers like from like 40 something machines. Now what we have is that on every rack switch, we have a /54 static route, /64 static route for every server. Then we summarize this to /54, because we can't really announce all these lots of routes upstream. We have to summarize them to /54. This allows you to have up to 1,000 routes per rack switch if you want to. We don't need right now, but it's possible to use them all. And so on, this being summarized upstream, and you get like 1 prefix per data center. This was very critical because we had to allocate new address blocks just to number every server additionally with /64 prefixes. I think basically we got a couple or a few more of /29s, but we allocate them in /32 blocks, and each /32 is sufficient to give you 30 data centers together. So it's pretty much enough space, thanks to IPv6, we have lots of numbers and addressing to cover. So this setup probably was most problematic to deploy because we had to reconfigure every single rack switch, every next pod switch, and so on and so forth. Pretty much every device in data center had to be updated to accommodate this. The good part is that this was very static. You pretty much have to allocate this once and then never touch it. OK, now host configuration. /64 per host sounds very easy. I think this took almost as long as it took us to configure every switch. Probably, I'd say we began deploying this in May. We finished this like in August or something, all this infrastructure numbering. It sounds easy. You have chef recipe which applies this. Unfortunately, configuring these new addresses broke some applications because people like to be fancy with the way we do things. And you also have to reapply this prefix on every new server deployment. This output shows the actual IP addressing from my dev server, development server. As you can see, we have IP address which says deprecated. Well, it doesn't mean we deprecate IPv6, of course. It only means that you set the lifetime for this prefix to be a 0. This is like not very well-known trick. It's kind of hidden in some RFCs. What this means, if a lifetime of a prefix is 0, the applications will not automatically choose it for address binding. So for example, if you do a connect outbound, you will not pick this address automatically. So this was very important because initially the connectivity to this prefix was broken. And if you make applications use this, you'll actually get broken applications. This still caused some issues because there are people who like to discover address on their own, and they chose this address by mistake. But overall, this went pretty smoothly. We did try our approaches. We did try to apply the prefix to a virtual interface, like dummy or TAN interface. That caused some other griefs. So in the end, we stopped on assigning this new /64 to physical NIC, ETH0. As you can see, the interface has 2 more addresses, link local and the old IPv6. There is no IPv4 if you even look at this. This server is purely IPv6. We now have lots of clusters and lots of data centers which are v6 only, becoming like a norm at Facebook. And this was just pretty much next step in addressing these machines. OK, so how do we get from this address per host to address per process? It's very straightforward. Now that you have ILA, you can randomly generate a /64 number and give it to the process. Say, hey, use a SER prefix and this random number as your address. And it sounds very simple, and there's chances of collision. But luckily, right now, with the /64-bit address space, the uniqueness is pretty much guaranteed, presented by the fact that it really takes a lot of time to get a collision in a 64-bit address space. So the next more tricky part is how would you make a process use this new address? Because people normally don't really bind to things, right? We just like, OK, bind to any, do connect, and expect things to work magically. And that's pretty much, I mean, good approach, of course. In our case, we had to somehow force this. So for people or processes which can cooperate, we give them a variable environment saying, this is your address, use it, right? For people who don't want to cooperate or cannot cooperate, we have this pretty ugly hack right now. You preload a shared library before process, and you make process use this guy. It intercepts bind, connect, and other calls, and forces the assignment or allocation of new address to be done automatically. So the application doesn't even know about this. They start business as usual, and they are forced to use the new address. This is kind of nice because it helps us avoid any need to change application. On the downside, if you break something, it's hard to debug because people often not very cognizant that you have the LD preload stacked before your application. Very popular right now in community, in public, in open source, namespaces. Namespaces and modules like IPVLAN, L2VLAN, they're great conceptually. They break lots of things right now for us. So we try this in some small experiments. We don't use this actively. So right now, if you look at all processes we run, they share the same namespace, default namespace on the Linux host. They just have different addresses they can use. OK, next is DNS support. People surprisingly don't like using addresses for like log output and other things. So they want these new unique addresses to have DNS names. Effectively, one DNS name per container or per process. Right now, we generate name on the fly when we start a new job or a new process. It looks something like this. It's pretty lengthy name. It uses like the local domain, which is typically used for like MDNS, multicast DNS. We kind of use this because it seems like a nice analogy of this virtual subnet where you have these addresses sharing 1/64. The very long name here says you, OK, this task runs in Prineville. It belongs to a team called Net Systems, and so on and so forth. And number 0 is number of a task in a global job. We only create Quad A and PTR records, straightforward, nothing fancy. And right now, this is a very custom hack. So we have, I think, with Unbound for DNS names, and then with a special process which accesses this backend database called ZPDB. ZPDB, I don't think is open source, but I think we spoke about this before. It's kind of, if you know this, similar to Amazon Dynamo. It's a global key value store, but allows you to create a key value pair somewhere and then read it elsewhere. It's really simple, not like super performant on writes because it has transactional semantic, but it works really well for us right now because the rate of change what we have isn't very high. OK, host support. This isn't like some magic what we did for ourselves. ILA is now supported in mainstream kernel. I think since version 4. I forgot what exactly, to be honest, we have a module called ILA. So this module implements ILA using the kernel routing table. If you're familiar, it uses the lightweight tunnels extension, which also allows you to attach other tunnel encapsulations, like VXLANs or MPLS. Lightweight tunnels is kind of this new framework in Linux kernel to do all this encap decap magic. All the API is Netlink. Netlink is OK if you like it. It's not as great if you kind of want reliability, but it allows you to, right now, create and populate mapping tables on Linux kernel machines. OK, so this will show you how you can configure a single host for ILA forwarding. So first of all, you load the module ILA. This is basically if you want to play with it at your home with the ILA configuration. You have to download the IP command, latest build. It has this option to, right now, define ILA encapsulation. So first command, of course, you configure the SIR prefix, SIR address, ILA address on your machine, on your loopback in this case. Pay attention, this orange stuff is the SIR prefix. Second one, you add static route, which tells, OK, for this other ID ILA locator, ILA address, use this encapsulation. So on the left here is the ILA address. On the right is /64 translation, the rewrite you have to apply. So when a packet hits this entry, it gets rewritten and flies away. And lastly, you have a mapping for incoming packets. So if a packet comes to your machine, and it has this locator and this identifier, so locator is red, identifier is green, you translate it back to the SIR prefix. So 3 commands, bind, route, and local translation. This is actually how it was initially. Initial implementation was simply using the IP command to create and remove entries. OK, ILA routers, as I mentioned, this is a big deal for ILA. Right now, we make every host ILA router. So every host which is part of ILA domain injects the SIR prefix. So you may have like thousands of machines which inject this /64 prefix and attract any kind of traffic to themselves. On one hand, it's kind of confusing. On the other hand, it gives you really nice load balancing. For traffic coming to a network, you can load share it across thousands of machines. We'll probably move to a model where we have dedicated machines for ILA routers. Right now, it seems to be easy to make everything very symmetric. Control plane. As I mentioned, the hosts have to inform the routers of the mappings. Once again, the slides have been truncated. On the bottom, you have ILA hosts, which are also ILA routers, just happen to be. When you start a new process, it gets new address, and it populates and writes to backend database saying, hey, this is my ID to locator mapping, and this is my DNS name. And then every machine simply downloads this every 5 seconds. It's really nothing fancy, right? It simply runs a busy loop, wakes up every 5 seconds, downloads mappings, and updates local table. These simple approaches are often more reliable than more fancy event-driven ones. It's not very reactive, obviously, because it may take like 5 to 6 seconds before you respond to a new mapping. But right now, it's sufficient for our needs. It's clearly not a standard, but works well for ourselves. And also notice this gets replicated everywhere globally at Facebook Network, because ZPDB is a database which runs globally across all data centers. Very, very simple, nothing standard. We definitely need something better in the future. OK. This briefly tells you about the scale of deployment. Right now, it's experimental. We tried this on a bunch of tasks. It's used in production in a very limited fashion. We definitely want to move forward with this globally. We'll probably have to hit much more obstacles in the future. Right now, things look promising, but you always get in trouble as you move forward. I mean, already we have discovered a few issues. Like ILA does this rewrites. And of course, this breaks the wonderful ICP messages on the transit paths. If you do a trace route, the host on the middle will send packets back, which have a payload that has the addresses which have been translated. The same for PMTU. So right now, this breaks some tools. We definitely have some work in progress to fix that, because operationally, people cannot tolerate trace route being broken or PMTU not working. Even though in data center, PMTU isn't such a big deal, it's really nice to have it working properly. OK, so the future of ILA is how we plan to develop and the next steps we plan to do. So first of all, more acronyms. You already know of ILA, ILNP, GSE. Next one is eBPF. I guess everyone here used BPF in their life in one way or another, because TCP dump is initially inherently built on BPF. So BPF is Berkeley Packet Filter. Spelled Berkeley right this time. Great. It's basically a language for packet filtering, used to be. eBPF is extension of the old BPF language called Classic BPF now. It's now JIT compiled. So it's bytecode which compiles to native instruction set in kernel. And it allows you to inject arbitrary code which runs a Linux kernel, not just filtering purposes, for much more different uses. And why it's a big deal for us is because it allows us to extend kernel functionality on the fly from user space. You can write something in this bytecode, you can inject it into kernel, and it's being invoked by kernel functions outside of user space. So for example use case is ILA router. Right now, we have application which implements ILA router purely as VPF program. So all these lookups, all these translations are done by a VPF program, which is simply uploaded into kernel and attached to inbound processing. Another abbreviation, that's the last one I promise, XDP. Express Data Path is a reasonably new development in a Linux kernel. It's a kind of response from kernel community to all this DPDK and our kernel bypass magic. It allows you to implement very simple and fast in-kernel networking. In a few words, you can attach eBPF programs very early in the driver code. You don't have to wait for full stack processing. You can inject code early in the kernel, and this allows you to implement functions with very low overhead. For example, ILA router attaches directly to a driver, and you don't have to walk through the full protocol processing chain. You don't have to go for routing table. You can process things very, very quickly. Of course, some limitations, but in a few words, XDP is a method to implement very fast networking in kernel. Well, just use cases right here. And obviously, if you have to, you can always punt from XDP program or a BPF program to a kernel for normal processing. And once again, this is reasonably new. I think it's been only around for like 8 months since this announcement. There's already support in kernel 4.6 and 4.8, I think, for a few drivers. There's much more work going on and lots of interest in the kernel community in the XDP functionality. OK. If you folks have to keep in mind a few things from this presentation, here we are. First of all, what's ILA? ILA is a thing that gives us unique address per process, allows us to provide location independence, And it all works on these two fundamental pillars, eBPF and XDP. And that's it. I'm done with acronyms, and I'm ready to take your questions. Thank you.
Matt Petak, Yahoo. Great work. I'm a little curious. You said it's every 5 seconds